Welcome, I'm very pleased you could join us today for my webinar on JESD204D. I'm Piotr Koziuk, I'm the product manager at Comcores APS for the IP core portfolio, and I will be sharing with you today my predictions for what the JESD204D standard will look like. The topic of this webinar is the future of JESD204, which is JESD204D. In this webinar, I will be making some predictions on what the new standard will contain. First, an introduction to Comcores. We are an IP core provider and we strive to offer the best-in-class IP components and solutions. The company stands on three legs: chip-to-chip, wireless, and Ethernet. And we have interesting IP in each category. Today, we'll be focusing on the new standard in the chip-to-chip interface area. I myself have over a decade of experience in building JESD204 IP cores. I started in 2012 doing RTL design. I have also led a team of engineers building Comcores JESD204 product. Now I'm doing product management for whole IP core portfolio. I'm also a member of JEDEC Task Group 16-4, which is doing standardization on the JESD204D. For a short recap of JESD204 history and origin, 15 years ago is when the first standard came out, with a single lane to a single converter device setup. The data rates were fast at 3.125 gigabits per second and 8-bit NB encoding. The A revision of the standard brought multiple lanes and synchronization between them. And then the B revision, which is still often used today, added deterministic latency and separated the clocks between the devices. The speed was also increased to 12.5 gigs, but 8-bit NB encoding was still being used. The C revision increased the line rates to 32 gigabits per second and changed the encoding to 6466B, which is exciting because it allowed for things like self-synchronizing receivers and extra bits for things like error detection or even error correction. Now the D revision will add new signaling of PAM4 for much higher line rates, up to 116 gigabits per second. This PAM4 signaling with its higher bit error rate requires RS-FEC encoding, and different FEC options will be provided depending on the lane reach. In this webinar, we will not discuss much of the JESD204 modes of operation, and I will assume you are familiar with the concepts of JESD204 framing and deterministic latency. I would like to spend as much time as possible with you predicting the new features of JESD204D. In case you would like a refresher on the JESD204 standard, please visit our website where you can view my previous webinar on this topic on demand. Here is a brief overview of the new features to expect in JESD204D. PAM4 signaling is the new signaling, but NRZ is still there. Each will be running at 58 gigabaud, meaning 116 gigabits per second in PAM4 and 58 gigabits per second in NRZ, or what we would call also PAM2. The standard will heavily rely on the OIF CI spec for the service requirements. And in PAM4, we will see the need for RS-FEC error correction. But in NRZ, we will only see the RS-FEC being used for error detection in place of the CRC mechanism. We will have Subclass 0, Subclass 1, and Subclass 3. And Subclass 3 will now be defined for systems using multi-ref instead of sysref for multi-point links. We will still have deterministic latency in Subclass 1 with the use of sysref, and the framing will be organized around FEC code words. Instead of sync header bits that we saw in 6466B encoding, there will now be a sync header burst used for boundary detection of FEC code words. And the data will be scrambled, and we will still have support for multiple converter devices aligned across multiple lane links, like before. And there's no changes in the transport layer, it will remain the same. Here on the right, you can see a picture that shows a payload that is being prepended by two symbols of the sync header burst and appended by the FEC parity bits. The big new thing for JESD204D will be the Reed-Solomon forward error correction encoding. It is required due to the high bit error rate on the PAM4 links, and depending on the link reach class, extreme short reach, medium reach, or long reach, different correction capabilities will be required. FEC1, FEC3, and FEC4 in the table here will be mandatory for the XSR, MR, LR classes, with FEC2 and FEC5 being optional. NRZ or PAM2 links will still use part of the FEC mechanism, but only for the error detection in place of the CRC mechanism from before. In the table, you can observe the different composition of the FEC modes. I will go into the details of these in a moment, but the key information to observe here is the overhead, which is in the mandatory classes 6.25%, and the correctable burst error length for each class. Now let's dive a little bit deeper into the world of Reed-Solomon forward error correction and how bytes become 10-bit FEC symbols, and how JESD204D will build FEC code words with sync header burst and parity symbols attached. A few new letters appear here that should be relevant in the standard. One of them is P, indicating how many payload bytes will make up a single FEC code word. This can be 160, 320, or 640 bytes. And assuming a single payload block is 160 bytes, we can say the FEC code word will carry 1, 2, or 4 payload blocks. In the image on the top right, we are demonstrating a single payload block inside of a FEC code word. So 160 bytes or 1280 bits will be represented as 128 10-bit symbols for FEC processing. These 10-bit symbols are the units of data that the FEC, RS-FEC uses, so we must do this conversion to understand the parameters. You can also see this when the FEC is defined like RS-FEC 136-130. The numbers here indicate the number of symbols in the FEC code word, 136, and the number of message symbols, 130. The message is 130 symbols because the RS-FEC also encodes the additional 2 symbols that are prepended to the payload as the sync header burst. I will explain the purpose of these 2 symbols in a moment, but just let's assume this happens. So 128 symbols in the payload becomes 130 symbols, 256 become 258, and 512 become 514 for the message. Now FEC1, which is RS-136-130 in this example, appends 6 more parity symbols to form the FEC code word. And the FEC mechanism is able to correct half of these parity symbols, so 3. And we say it means it can correct up to a 21-bit burst because that is the longest burst that spans 3 10-bit symbols if the bit burst starts on the last bit of the first symbol. This graphic should demonstrate how these FEC code words are put together in all different 5 FEC modes. For this demonstration, let's assume our frames consist of 8 octets, but they really don't have to. It just makes this image cleaner. But the important part here is that we take frame data and group it into payload blocks of 160 bytes. You can see these gray blocks here. And then the RS-FEC, when it's encoding this data, it works on symbols. So we can see the transition from 160 byte blocks, or a number of them, into the payloads in blue. These payloads will get prepended with the sync header burst of 2 symbols. And this sync header burst carries a constant bit pattern and an end of alignment block indication inside of it. And finally, this as a message gets passed to the RS-FEC encoder, and different lengths of FEC parity gets appended onto the end of the message to form the FEC code word, depending on which FEC mode is being used. These FEC code words are then sent across the serial link into the receiver, where the receiver will look for the pattern of the sync header burst to align to the FEC code word before passing the data to the FEC for processing. Now let's discuss lane alignment and how that might be handled. From JESD204C, we know we had a large framing structure called extended multi-block with the E parameter, and in JESD204B we had the multi-frame with the K parameter. And now in JESD204D there's a new parameter called A, and it will serve a similar function indicating how many 160 byte payload blocks will form a single alignment block. So this is our major framing structure, the alignment block. And A will take a value from 1 to 32, and the resulting alignment block must hold an integer number of frames. Since we'll be aligning on an alignment block boundary, it must be ensured that each alignment block starts with a whole frame. That way we always start deframing correctly. In the figure below, A is set to 2, and we can see in orange the sync header burst with the end of alignment block indication happening every second FEC code word, as each code word carries only a single payload block and the alignment block consists of 2 payload blocks. The blue arrows show where the alignment block boundaries are indicated by a sync header burst with the end of alignment block indication. So this is a simple example. And now let's move to a little bit more difficult one. It will not always be the case that the alignment block boundary coincides with a sync header burst. In this example, we set F to 12, meaning our frame consists of 12 octets, and frames no longer nicely align with each FEC code word payload. In this example, the FEC code word payload consists of 4 payload blocks, and we set our alignment block to contain 3 payload blocks. Containing 3 payload blocks allows it to align with a whole frame or start with a whole frame every time. But the FEC code word contains 4 payload blocks, and it will consist of the first one, where you can see the color change from orange to gray or yellow to gray. It actually, you can see maybe part of the frame is in one payload block and the other part is the next payload block, right? And again, the payloads will be RS-FEC encoded with sync header burst and parity symbols added. And on the bottom, we can see that not every alignment block will now fall on a FEC code word boundary and be covered with a sync header burst. So it cannot be indicated by an end of alignment block indication in that sync header burst. But those sync header bursts, the orange ones, will happen occasionally, right? And because we know A is equal to 3, we can imply the other boundaries that happen actually in the middle of the FEC code word payloads, as indicated by the gray arrows in this image. I will briefly touch on the topic of deterministic latency and the new subclass 3. This might seem familiar to those of you that have studied the JESD204C spec, as subclass 3 multi-ref mechanism already existed in the JSD specification. In JESD204D, however, it will receive its own designation of subclass 3. And we are skipping from 0 to 1 to 3 because subclass 2 already existed in JESD204B. It made use of a sync pin that no longer exists in these self-synchronizing receivers. So that's why there's this odd skip. In subclass 0, there is no deterministic latency and there is no way to align multiple converter devices data when they're separate devices. The data from the disk queue buffer is released as soon as all lanes provide the data in that specific device. In subclass 1, as before, sysref, that is in sync with the device clock, is distributed to all the components in the system, giving a precise timing reference allowing for deterministic latency. And in subclass 3, there is no deterministic latency, however, a multi-ref signal is shared across devices on a multi-point link, allowing them to have a common local reference used for aligning lanes on a common local alignment clock boundary, LAC. I would like to take this opportunity now to briefly mention how Comcores JESD204 IP core can enable you to take advantage of the new JESD204D Standard features. Our IP core is fully customizable and now also features the new JESD204D RS-FEC link layer. It can at the same time support JESD204C and JESD204B with the other link layers and the common transport layer. Comcores is very easy to work with, and we are open to doing changes to our IP core with custom features and with wrappers and on customer requests. We deliver our core with RTL system Verilog test bench that helps engineers instantiate and get familiar with our IP core. We also offer a UVM-based VIP and an integrated test environment. We are in tune with our customers' pain points, and we are aware of the challenges of PHY integration, and we have solutions for that, which I will mention in a moment. Our IP has been through many interoperability tests with both converter and PHY vendors. And we have a fantastic and responsive support and where you can reach the engineers that work on the IP code through our service desk if necessary. We also offer JSD training for your team. And finally, the biggest testament to the quality of our product is the large amount of return business from our customers worldwide. I mentioned solving customer pain points on the previous slide, and I would like to expand on this topic as it is a new initiative for us. Our experience with over 50 commercial projects allows us to understand how challenging PHY integration can be for our customers. So we decided to invest the time to help the best we can in mitigating this pain point by creating a PHY integration guide. This will be a compendium of knowledge, of our integration knowledge on the topic. And we understand that maybe this document itself might not be enough, so we are also offering additional guidance or even engineering resources to tackle the task of PHY integration. And out of these efforts, we are expecting to be able to offer off-the-shelf integrated packages with the leading PHY models from the PHY vendor partners that we're working with. And now let's move to some question and answer time, where I would like to answer some questions that came in through the chat. So first question on my list is, will JESD204D be backwards compatible with 204C? And the answer is most likely the standard will not include backwards compatibility with JESD204C. However, that does not mean devices could not be built that are backwards compatible. For example, Comcores JESD204 IP core will include link layers for both the D, the C, and the B, and those can be chosen at compile time, so you can have a device that has support for all three standards. All right, the next question is, what is the purpose of subclass 3? And as I mentioned before, subclass 3 is really what we called subclass 1 with multi-ref in the previous standard. And it's useful when you don't have a sysref signal, but you want to align multiple devices on the TX or RX side with each other, right? And you can have one of those devices issue a signal as a multi-ref master, and the other devices consume it, and that way you can synchronize the multiple lanes of different devices together, right? But it does not offer deterministic latency, so it's a little bit like a localized sysref, right? To basically have a common timing reference on one side of the communication, but it doesn't offer an option for deterministic latency. Okay. Next question is, what is the purpose of the optional FEC2 and FEC5? Okay, so I mentioned before that FEC 2 and FEC 5 would not be mandatory. So FEC 2 is a little bit stronger version of FEC 1, so it allows to correct more errors, but I believe it also has a larger overhead, so there's a penalty for that, ability to correct more errors. And FEC 5 is actually a lighter version of FEC 4, where it will correct less, but on the other hand use less resources and maybe have less latency together with that. So it is a alternative to use. Maybe if you have a more noisy, less noisy link, you can select to use a different FEC option there. Okay. And the last question here that I have is, can you explain more about the LAC? And I briefly mentioned that in one of the slides, that this is the local alignment clock, and it's very similar to what LEMC was, or so it's local extended multi-clock, or LMFC, local multi-frame clock. So those clocks basically are, in our case, there are internal counters that dictate the timing for multi-frames, extended alignment blocks, or in this case extended multi-blocks, or in this case local alignment clock. So it dictates the timing for the alignment blocks. So once you find an alignment block, you know that in a specific amount of time the next one will appear. So that is basically the local alignment clock. And if you're using sysrev, then sysrev or multirev, those will sort of be a starting point reference for the local alignment clock, and that will dictate the timing of your framing internally, so everything can align. So that will be it for question answer time. I want to thank you all very much for attending the webinar, and if I haven't gotten to your questions, I will answer them over email. I'm really looking forward to hearing from you and working together on your projects, where Comcores will supply the JESD204D interface IP. Please send us an email at sales@comcores.com for more details on our product, and thank you very much for your attention, and have a great day.